Okay, we're continuing on here, chapter 2, still. So obviously last time we talked about, I think, measurements. We also talked about significant figures, doing calculations with significant figures. Towards the end there, we were again talking about sort of our prefixes, and also a little bit, I think, about how to sort of set up problems through what's known as dimensional analysis, which we'll talk a little bit more about, I think, today as well. Remember that when we do use those prefixes from that table, and again, it says something like centi is our 10 to the minus 2, our kilo is 10 to the 3, it's 10 to the minus, excuse me, 10 to the minus 9. These again are the amounts there are in the base unit to, again, one of the prefix units. And it really doesn't matter what the actual unit is. The prefix really kind of determines what it is. Also, a reminder that when you see it sort of written like this, that's really scientific notation, and it's really 1 times 10 to the whatever any of those guys are. And that's how you would punch it into your calculator, like we talked about using your exponent button if you need to do so. So again, if we had something like 4.64 times 10 to the minus 7 meters, and we want to know how many nanometers that is, we could use our nano sort of prefix here to help us solve that. The base unit here is meters, as it's obviously in both of them, and this is the proper way to use the equality is in one of the prefix units, which in this case is the nanometers. There is 10 to the minus 9 of the base unit, which is meters. I think we touched upon this last time as well. This is was again referred to as an equality. An equality, again, basically represents two values that are on different scales, but they do represent really the same amount of whatever we're talking about. In this case, it really represents the same amount of length in each case for each of those. The kind of benefit or purpose of an equality is it does provide us what are known as conversion factors that we can use in the calculation. And a conversion factor is really just two fractions that you make from the equality, where you basically put one value up on top and the other on the bottom, or you can flip it like top and the other guy there on the bottom. So when we do problems in chemistry, as we talked about, I think towards the end there, we do want to kind of follow dimensional analysis, which is essentially using conversion factors. And the idea really behind sort of working problems out in this fashion is we're essentially just trying to get rid of any unit that we no longer want, and we want to end up with replacing it with units that we actually do want at the end. And it's the conversion factors that allow us to do that. When we do this type of calculation, pretty much all we're going to be doing is multiplying and dividing. So if we take our original number here, 4.64 times 10 to the minus 7 meters, remember that we want to set it up so that we can see everything canceling out in terms of the units. And if you're just starting with one sort of value by itself, although it is not really a fraction, if it helps you visualize where everybody is, you can put it over 1 so you could clearly see that meters, which is the unit we really want to get rid of, is up on top. And it's really simple when you do dimensional analysis to get rid of things. You basically just put the exact same unit in the opposite location, and that will essentially get rid of that unit and sort of cancel it out. So in this case, we actually do need meters on the bottom, so everything works out right. So we will have something like that guy there, conversion factor we're going to use. By the way, you don't use both conversion factors in the calculation. Otherwise, you're going to undo your calculation, basically. And again, in this case, mathematically, as we spoke about, what we're going to basically be doing is anything that's up on top, again, we're going to multiply, and anything on the bottom eventually gets divided. So we just basically multiply whatever we got going on top, get to the end, and then come back and divide by whatever we have on the bottom. What that essentially does mean is we have meters on top that we're going to divide out with the meters on the bottom, and they will cancel each other out. So as I mentioned last time, it's kind of similar to meters over meters equals 1, just like if you took 2 divided by 2, those guys would cancel out basically and make 1. So the units basically cancel out the same way. That leaves us the only unit that is left, which is nanometers, and that is on top, which is really important because if you are solving for some type of unit, and it's just one unit by itself, it does need to end up on top for it to be correct. So in this case, we're actually just going to divide the two numbers because we basically just have 1 on the top there. So we're going to take 4.64. We want to make sure we use our exponent button, our negative button, and 7. We then want to divide it by, once again, that is basically 1 times 10 to the minus 9 on the bottom. Also, you want to put it in your calculator, probably in scientific notation, depending on your calculator. Again, 1 exponent button, negative button, and 9, basically. And that's going to get us here 464 nanometers as our answer. Again, in terms of sort of significant figures, one of the nice things as well about sort of dimensional analysis sort of calculations is you are essentially only multiplying and dividing, which means in most cases, you're just going to probably end up with the least number of sig figs, which would be this guy, and that would be 3, which is what we do end up with. This definition or conversion factor is considered an exact number, which means when we do calculations, we don't have to worry about, how many significant figures that particular one has. We can kind of ignore it in terms of deciding, what our answer should be. Question on that one there. I think we also did one where we went kind of prefix to prefix at the very end last time. And again, as I mentioned, I think in that example last time, it's a really good idea to, if you're going to do some type of conversion, kind of like from a prefix to a prefix, I think we might have did millimeters to kilometers or something like that. I think we did. And the best thing to do is always sort of take the first prefix back to the base unit, because you can look it up in that table and find like what the prefix means. You can very easily take it back to the base unit. And then you could also then find very easily in that table from the base unit to the next prefix unit. So that's usually a really good sort of method of going kind of from one prefix to the next, is to just take it back to the kind of base unit and go from the base unit to the next one. Any questions on any of that stuff? Yeah.
So on the following to the 0.64 times 10, when you enter that, do I put 1 exponent -7 or just 7?
It is -7 the exponent on the original number. So for example, you would punch in something like this, 4.64. You would hit your exponent button, like your negative button, and then 7. Yeah. And that will get you probably something that looks like on your calculator like this, or something that looks like, that. That's the actual answer. That's what you get when you punch this number in, and then you got to divide it by this number on the bottom. So we have to divide it by that number, which would also be kind of scientific notation, 1 times 10 to the minus 9. So that's the end result of that sort of problem there, is the answer is just 464 nanometers in this particular case. Other questions? Okay, let's continue on. So we've been talking about equalities, and again, as I mentioned, they are related to each other, as they do represent the same amount of whatever you're looking at. But again, they are just on different sort of unit scales. So for length, these are some common equalities that we do see a lot that pops up. 1 meter is 100 centimeters. So that again is something that does come up a lot. That is sort of the whole number version of what we do with centi, which is 10 to the minus 2. And in 1 centimeter, there would be 10 to the minus 2 meters. The way you get to this number is actually you divide 10 to the minus 2 to both sides. Those cancel, gives you 1 meter on this side equals 100 centimeters. So they're both really the exact same conversion. It's just looking in the first example, 1 centimeter is 10 to the minus 2 meters. How many meters there are in a centimeter? And the second one is how many centimeters there are in a meter. So they basically represent the same thing. I would say that's something good to know, right? 1 centimeter is 10 millimeters. That is again on the bottom of the ruler. You got 10 little dashes before you hit a centimeter, and that's what those little dashes represent. I would say 1,000 kilometers is equal to 1 meter is another sort of equality that we use a lot for length. So I would say probably the centimeters to meters, the kilometers to meters are two very common sort of equalities that we use, again, to convert between different length type units. Now, in terms of volumes, I would say probably that's going to be your big one right there in terms of equalities that you'll use the most. That is probably 99.9% of the time the conversion that you would use if you're kind of converting units of volume. And the real reason for that is very commonly in the laboratory, like you will probably do in some experiments, when you sort of record the volume or sort of figure out what the volume of a solution is. A lot of times you do record it in milliliters. The problem with that in some cases, or in a lot of cases in chemistry, is when you need to use the volume in sort of formulas, it oftentimes needs to be in liters. So kind of going from milliliters to liters is a very common one. Going from liters to milliliters is also very common as well. You probably won't see too much deciliters or anything like that. There's some paper towels if anybody needs. We also saw that cubic centimeters. Paper towels? Yeah. Another very common unit of volume is cubic centimeters, which is 1 cubic centimeter is actually, again, the same as 1 milliliter. So it is sort of a one-to-one conversion between those two things. And a cubic centimeter is a volume. We have here like a cube or something like that. Again, if you take sort of 3 length measurements and you measure each of them in normal length measurements like centimeters, and you multiply them together, you do get cubic centimeters, which is a volume. So basically, if you take any type of length measurement and you cube it, it will be basically a volume if you're talking about a cube. That's a very common way that we get the volume of like a solid object, is just to kind of measure in 3 different directions with a ruler. Sort of in medicine, a cc is also a cubic centimeter. That's oftentimes used for like injections, like and give somebody 5 cc's of this or 3 cc's of this, before they die. That is basically a milliliter and stuff. I know these are pleasant thoughts as I speak that to help them have a nice day. We'll just put it that way. Cubic centimeters, cc is used a lot with, again, like I said, syringes are oftentimes labeled as cc's and stuff like that. There it is, speaking of it, right there. So again, all these are essentially equivalent to each other. We do see cubic centimeters a lot when we talk about density, and which we will towards the end of this chapter. Common units of density are grams per milliliter or grams per cubic centimeter. So we do use that interchangeably along the way. Mass equalities that definitely we probably run across a lot. Kilogram, kilo's 1,000, so that's 1,000 grams, and a kilogram is something that we see a lot. 1 gram is milligrams as well. Your book uses a weird symbol for this. That is, I believe, micrograms, but most people, that's the micro symbol. But your book is like MCG. It always confuses me every time I see it. I'm like, what are they trying to do there? So I believe that's micrograms, what they're trying to do with that. For all equalities, so any of these that we see here, again, use some type of calculation that you can basically set any of these guys up as conversion factors for every equality that you have. Very common mass equalities that we'll see a lot. Find the larger unit, millimeter, it, I guess. Microgram or gram. Okay, so let's take a look. Millicenti, we're looking for larger one. So a centimeter, right? It's going to be larger. Again, if you just think about a ruler, the smaller markings on the bottom are millimeters. The ones that have numbers, which are the larger markings, are centimeters. Kilogram, centigram should be, sounds good. Kilo is 1,000, right? Deciliter, microliter. Yeah, deciliter. Microgram, milligram. Milligram, I think, should be larger in that case. Yeah. Again, those should be our our units. See, again, I don't know why they use the symbol on the top one, but not this one, but I don't know. So it's kind of, again, if you had MCG or MC, they use microgram. They kind of use this symbol. But clearly they had it in the computer. They're able to do it on the one above, so I don't know. This is microliter. That little symbol is, yeah, the little symbol really is micro. And clearly they had it somewhere there in the computer to use it there. But down here, as you can see, they use like this, which they commonly do. So just watch out for that. I don't anticipate we see too much, but you might in some of the homework problems like that they kind of those symbols kind of back and forth. Indicate the units that completes the following. So take a moment there. All right, so if we take a look, that's 1,000 meters equals something. So 1,000 is really the kilo, right? Sort of prefix, right? Those 10 to the 3. Zeros, you have 1,000, right? So that should be kilos 1,000, basically, yeah. Here we have 0.01 meters. So again, if it's helpful, it might be if we kind of turn that into scientific notation. 1, 2, that is 1 times 10 to the minus 2, or 10 to the minus 2, which we saw earlier was centi, right? So I'm thinking that's going to be the centimeter there. So any questions on that there? Okay. All right. So that means here 1 kilogram should be, kilo is 1,000 grams, yeah. And 0.01 centiliters. So let's see. So we know this is centi, right? So if we think about what centi means, if we just kind of do it like we talked about, centi is 10 to the minus 2, right? So in this case, if regardless of the problem that we're looking at, if we were just going to try to find the relationship between centiliter and liter, that is how much there is in the base unit to one of the prefix units. So 1 centiliter will 10 to the minus 2 liters, but we want this, right? So divide by, see what we get when we do that. By the way, we'll take 1 divided by 10 to the minus 2, and that should give us 100 in this case. So there's 100 centiliters in 1 liter. So we can use this as like a conversion factor. We actually could just use this as a conversion factor. So if we go 0.01 centiliters, we could do a little dimensional analysis. To get rid of centiliters, we'll need it on the bottom. So Again, 1 centiliter is 10 to the minus 2 liters, which means I could have 1 centiliter over 10 to the minus 2 liters. Our 10 to the minus 2 liters is 1 centiliter. So in this case, we do want to use a conversion like this that we could get from that equality. And 1 centiliter, these guys will cancel. So we'll take 0.01 times 10, 1 times 10 to the minus 2, and we will get 0.001 liters, right? Which I believe somebody said earlier. So there it is. So again, we could use our conversion if you can't see it directly and just do a little dimensional analysis with it and choose our two questions on that one there. I feel like they chose the wrong one there. I feel like they circled the wrong one unless I punched it in wrong. Let me try that again. I don't think so. There you go. I think they selected the wrong one on that one. So it should be the first one like we got there. All right. Yeah, sort of been doing intertwining here with what we've been talking about. Again, conversion factors, as we've been using them and talking about, comes from equalities. Now, when we use conversion factors and we get them from equalities, remember there are two types of sort of units that we have. We have kind of English units or US units and metric units. And remember that for the most part, if you are using any type of conversion factor that comes from a equality, that is again an English to English one, or a metric to metric conversion, all these guys are considered exact numbers. Like when we sort of get our answer and do our calculation, we don't have to take any of those into account in terms of where we should do our significant figures last time, right? So when we multiply and divide, we look for the least number of significant figures, and that's what your answer have. When you add or subtract, you're looking for the least number of decimal places, which again is what your answer should have. Now, when you use conversion factors and dimensional analysis, which is pretty much where you'll use it the most often, really the only thing that you're doing mathematically speaking is multiplying and dividing. And that means that you'd be looking at significant figures and you would not have to worry about the significant figures in the conversion factor. The only place where if you take an equality that you will have to sort of consider the significant figures in that conversion factor that comes from that equality is, technically speaking, if you cross over from metric to English or back and forth. So if you find yourself in a calculation where you're using really a metric to English sort of conversion factor, you do need to take into account the significant figures. So this is typically not considered an exact number when you're using conversion factor. There is a few that are considered exactly crossover, and probably the most centimeters. So this one is sort of an exception to the metric to English sort of conversion. If you do have that one, you could ignore it. You don't have to worry about it. The idea there is, again, as we talked about, I think, exact numbers basically could have as many significant figures as you like. And because of that, there is kind of no rule that everybody can follow with them, as I may say 4, you may say 3, somebody else may say 120, whatever they want to use. So with that, to make sort of a rule that everybody can follow when they're using a conversion factor, that is an exact number, you basically just kind of throw them out. You don't have to worry about it in terms of your answer. So we have metric to metric here, right? Meters to millimeters. That's an exact. We got a pound to 16 ounces. That's an exact, as that's an English to English. And then we also have a crossover here, which is 1 kilogram is 2.2 pounds. So we would have to, in most cases, for example, if we were to use this conversion factor, either one of these in either sort of form here, you typically would have to kind of consider the significant figures in this conversion. Look at this here. One of the numbers that's actually a 1, so you don't worry about that guy. So you would be looking at like the significant figures and the other number that's kind of like a real number other than 1. So this guy would be carrying kind of 3 significant figures if you're doing some type of calculation. And again, if that ended up being the least number of significant figures, then that's what your answer should have. I would say probably in most cases, start with is probably either the correct number of significant figures or pretty darn close to where you should end up with. In most cases, not 100% of the time, but probably early mid 90s% of the time. If all you're doing is some conversion factors and stuff like that, probably that original number is pretty close to what you should have in terms of significant figures for your answer. Qualities on food labels, again, listed both in metric and US, as you can see there, right? In parentheses, we got the metric and we have the other on the US on the packaging there. Qualities and significant figures. So as I mentioned before, anything where we're going and keeping basically metric to metric, English to English, you could just no-brain it and just not worry about it. Again, just that metric to English, you got to kind of take a moment and do that. So all these would be considered exact numbers, and you do not need to worry about them in determining your answer there. Here again is our crossover, as I talked about. These are not going to be considered, again, exact numbers here because we're crossing over. Once again, if we're looking in the calculation to try to determine significant figures, we would want to be looking at this guy in terms of this conversion factor, which would have 3. We would look at this number, which has 3, and we would also look at this number, which has 3. So again, I think your book kind of rolls with pretty much just this one as being the exact number and a metric to English crossover sort of event there. All right, so we've talked about this, that conversion factors are really just fractions that we use in dimensional analysis, again, to get rid of the units that we don't want and keep the units that we do want. Now, you do have to remember that I think we've done some examples here where we've obviously done some conversion factors and converted some units, but sometimes you do have more than one unit that you might need to convert. So for example, let's just say I had, let's just say I did 45 miles per minute. So maybe I'm moving 45 miles per minute. That's pretty fast. So we're going to move 45 miles per minute. And let's just say that I wanted to know how many like feet per second that was, for example. And in this case, when we try to do a conversion, there actually are different ways that you could get to the end result, depending on sort of the pathway that you choose. What you want to sort of think about, for example, is, how can I get there? And sometimes you want to think about maybe how can I get to the unit I want in like the shortest distance, but you can't take a long trip, right? They both get you there, right? If you take the shortcut, usually you don't get lost, or you take the really long way around, right? They all get you to the same location at the end if it's the correct sort of direction, either one. So really we want maybe some way to go from miles to feet, and maybe we know that. Maybe we know that there are 5,280 feet in a mile, and that is our equality. And from that equality, we obviously can have 2 conversion factors, one that looks like this, or again, the other one is just the fraction reversed. Now, we also need, in addition to converting our miles to feet, we also got to get ourselves from minutes to seconds, which hopefully we know that in 1 minute, right? There is 60 seconds, I hope, right? So that is our equality there. And that also will give us a couple conversion factors that we could use. So again, here, the benefit of setting things up in dimensional analysis so that you can see the units is a problem like this where you have a lot of units that you need to convert, both top and bottom. And the benefit of doing that is it allows you to know pretty much where everything is. So we do want to kind of set it up, and I would set it up very much like a fraction where it is very clear what unit's on top and what unit is on the bottom. And this is the benefit of doing this, because remember that when we do dimensional analysis, we really don't have to think about it. All we have to remember is opposite, right? So opposite gets rid of the units that we need to get rid of. So in this case, we could clearly see, for example, miles is on top, and we want to get rid of miles. So all we have to know is opposite, which means we definitely want to use that conversion factor there to start with, perhaps. And if we do that, again, keeping top and bottom sort of separated correctly, 5,280 feet in a mile. If I stop the calculation right at this point, what units do I have? The miles do cancel, which means I now have feet over minutes, which means I am halfway there, right? I've converted the top part, right? So all that's left is the bottom part that I need to do. So this is really where dimensional analysis comes into play really well, because I cannot tell you how many times students, when they have a problem such as this, and maybe that bottom one is like and they need to get to hours, so maybe they got to do like, seconds to minutes, minutes to hours. They really do not know what they should do. And what I mean by that is they don't know if they should be multiplying and dividing, and very commonly people do the wrong thing. And that is because they don't set it up like this, and they're just trying to figure out after they kind of write some stuff on the paper, I'm not really sure. Maybe I'll just multiply or divide. Here it should be pretty much, again, a no-brain situation. You should visually see what you should do, and setting it up like this allows you. I could clearly see, right, I need to get rid of minutes, and I could clearly see my minutes are on the bottom, right? So going opposite to get rid of it, I need minutes up on top, which that pretty much eliminates any question of what conversion factor I should use, because that's the only one that has minutes on top, right? So I'm going to put my minutes up there on top. I'm going to put my seconds on the bottom. My minutes will cancel. And now I am left with feet on top and seconds on the bottom, which is exactly really what I'm looking for. Any questions on that? Now, why this is also really good to do is because if you understand simply how to do a dimensional analysis problem, which frankly just means, what do I do with every number on top? I should do what with those numbers? Multiply them, right? So now I don't have to worry about, should I be multiplying and dividing? I know it's on top, so I automatically know all I have to do is multiply whatever is up on top. And I also know anything on the bottom gets divided, right? So it kind of takes the guesswork out of it, right? Because you have it all set up and you just know, hey, I'm multiplying everything on top and I'm coming back through and dividing by the bottom. I know I'm doing it right because all the proper units cancel out. You got everybody set up right. So it just sets you up for success with the calculator, and you hopefully won't multiply when you divide or divide when you should be multiplying by doing it this way. So if we do this, clearly we're going to take 45 in this case. We're going to multiply it by 5,280. And that's all I got going on top. So I'm going to hit equals. Then I'm going to come back and divide what's on the bottom. Now, clearly there's no numbers here, but these basically represent ones, which means you don't really have to worry about it in terms of putting it into the calculator, because you're just going to get the same number, obviously. So really the only thing we have to divide by here is our 60. So we'll divide it by 60. And that's going to get us here. I'll agree with you, 3960. Now, in terms of the units, we have feet on top and we have seconds on the bottom, right? And again, the number should go with the top unit, and the bottom unit usually is 1, so it doesn't usually have a number when you get it out there. Now, I circled it. Probably shouldn't have done that, right? Because the other thing I should look at is, do I have the right number of significant figures in my answer? The one that I circled, does it have the right number of significant figures? The answer is probably no if I'm asking that question, I imagine, right? So it probably does not. And we want to think about, what we need to look at here in terms of what our answer should be. Again, the additional benefit of doing it like this, which you should do, is again, all you're doing is multiplying and dividing always when you set it up like this. So that also should just limit you to, okay, I got to look at significant figures. So that's what I need to look at here. That's the important thing in terms of our answer. So clearly this guy here, do I need to worry about in terms of significant figures? I don't. That's an exact conversion, right? So you don't have to worry about that one. How about this one? Feet of miles. No, those are English, right? Well, our English, I suppose. Not if you go to England, it's not. It's kilometers and stuff. But here in America, in the U.S., it's feet of miles are the same sort of type of unit in terms of English or U.S. unit. So that does default us back here to really, like I said before, a lot of times, kind of that original number a number of times is really kind of the right thing. That guy has how many? 2. That means that my answer actually should have 2 significant figures. Oh boy, look at this one. So we're gonna go there for 2. I look at the 6, which means I need to round up. So that's gonna really round up to 4,000 feet per second. Do I have the right sig figs now? I don't. I only have, this is a number where can I write it in decimal form and get 2 significant figures and still have the right answer? No, that part of it is no. You could write 2 significant figures, but you won't have the right answer. So this is a number clearly, again, if you wrote 40 and 4,000 is not the same number, right? So although it does have 2 significant figures, you definitely got the wrong number or value there. You put a decimal point at the end, you got 4, right? You got no decimal point, you got 1. So this is a situation where really the only way we can get the right number of significant figures, and I just made up these numbers, got lucky, I guess, on that part of it, I suppose, is to go scientific notation at this point, right? So remember, that has to be a number between 1 and 10. So we got to roll 1, 2, 3 places and go 4.0 times 10 to the 3 feet per second. Now I think I can safely put a circle around that. Maybe it will let me, maybe I'm in a happy face at this point that I have no more room on the page to write at this point. Any questions on those steps? So I can't stress enough to set yourself up like this, because like I said, I see a lot on exams and quizzes, and people have sort of the right idea how to set it up, but again, they're not very careful on kind of like top and bottom. And again, they start multiplying when they should be dividing, or dividing when it should be multiplying. So if you just kind of set yourself up here, like I said, it can be like a no-brainer type situation. You just kind of, I know, multiply on top, divide on the bottom, opposites cancel. So it's kind of like only 3 things you have to remember when you do these calculations: multiply top, divide bottom, opposites cancel, right? So that's just an easy way to remember it. And that's what you kind of want. You want to kind of set yourself up right for success. And that comes with showing your work correctly. It helps you immensely when you go do the calculation. Any questions on that there? All right. So speaking of some equalities, here's a bunch of equalities. And like I said, everybody in this column is going to be an exact. Everybody in this column will be an exact. And pretty much only this guy will be exact. Here we do have to think about significant figures. If we use anybody pretty much down this way into this column. So again, a lot of times it will still probably be that first number, but you should definitely take a look at it if you see a metric to English sort of conversion. They will be provided for you. Just need to be able to kind of use it correctly. Yes. Okay. All right. So we sort of touched upon this, so we might just go a little quicker through some of these. But again, we have our equality of 1 meter equals 100 centimeters. Again, you could always get 2 conversion factors. And again, you should only use 1 in a problem, the same problem. Otherwise, you're undoing your work. Yeah. And again, our metric here, as I mentioned before, if we were using this in a calculation, we would have to take a peek at those significant figures to see if it affects where our answer should be. Once again, this guy would be an exact conversion that we don't need to do that. So we'll take a look at some of these here. So 1 liter is 1,000 milliliters. And again, that is one that we do use a lot. So you might want to commit that one to memory because it really does pop up a lot in chemistry. So you'll use it a lot. So the nice thing, by the way, if you remember that one, by the way, it really is remembering, for example, milli, right, is what it is. And it doesn't really matter the unit. So, you know, if I had 1 gram, that would be how many milligrams? It would be the same, right? So it works for any unit you want. You know, so you could kind of substitute the unit if you see the milli there and use the same sort of conversion. Same thing with the kilo, right? 1,000 kilometers in a 1,000 meters in a kilometer, 1,000 grams in a kilogram. You know, it doesn't really matter the base unit as you go through there. There's our 39.4 inches is a meter, and again, this one would need you to look at that if you're going to use it in a calculation in terms of the significant figures. And there's our milligrams, again, back to micrograms maybe in this case. And we got 1,000 micrograms is 1 milligram as well. This would be a basically metric to metric, so that would be an exact number. So you wouldn't have to worry about any numbers in there. All right. Now, some places, by the way, when you have problems, sometimes you're actually given conversion factors within the problem. And in this case, for example, a car travels at 85 kilometers per hour. There's England, right? If we're driving in there. So if you're given something like that, clearly that's not an exact conversion, right? So cars don't always go 85 kilometers per hour, or you don't always drive 70 miles per hour, I hope. All right. So if you're typically given some type of information within a problem that you're going to use as a conversion factor, you typically do need to kind of look at the significant figures when you're doing the calculation. So that's what this is basically saying. You know, if you have something like 85 miles per hour, 85 kilometers per hour, if you have something per something, those are basically 2 units, right? So here we have kilometers per hour, basically means kilometers on top, which will usually keep the number, and hour on the bottom, which it basically has 1. But when we use it as a conversion factor, this would have 2 significant figures that we would have to take into account if we were using it in a calculation. So we can't ignore that one again, because it's probably was specific for that situation and give it to you in the problem. A tablet contains 500 milligrams of vitamin C. Again, here, not all tablets have 500 milligrams, right? Other pills may have different dosages as well. So that's not an exact conversion that's specific for this particular vitamin C tablet. So again, we can convert that into a conversion factor. It's basically telling you, as you can see there, there are 500 milligrams in 1 tablet. You again could flip it around and go 1 tablet has 500 milligrams, right? In this case, we would need, once again, to look at that value, as it is not an exact number and really specific for that problem in that situation. In that case, it actually only has 1 in that case. So, you know, that might actually be what you might have to end up with in terms of your significant figures in your answer. Percentages as well is a very common thing that I think we might have talked about a little bit earlier as well. But if you're given a percentage and you want to turn it into a conversion factor, again, the best way to do that is to assume you have 100 of whatever you're talking about. And the purpose of that is it basically will keep the number the same. So again, if you got 80% on your exam, you probably got like 80 points out of 100, right? So that's an easy way to turn it into sort of usable type numbers. So if somebody has 18% body fat by body mass, that basically means if you're going kilogram way, 18 kilograms of body fat per 100 kilograms of body mass, or 100 kilograms of body mass to 18. The 18 is measured and has two significant figures. The 100 is exact. So this guy would be rolling more with this number in terms of significant figures, as we sort of arbitrarily assign exactly 100 to get us that sort of relationship. By the way, if we were doing more of an English type of conversion with that, that would be like 18 pounds of body fat per 100 pounds of body mass, right? You can kind of do pounds to pounds. You could also do like grams to grams if you want, kilograms to kilograms. You can really do any type of unit that you want, as long as they're the same on top and bottom. And then obviously here's some doses. So a little Keflex, an antibiotic, available in a 250 milligram capsules. That again means there's 250 milligrams in every tablet that you have. And again, that 250 we would have to look at in terms of significant figures here. Any questions on any of those there? All right, so again, looking at some of these sort of conversions that we get. 1 meter, there's 10 decimeters. And again, we could get our two conversion factors. That one would be considered exact in that top one, as they're both metric units. Gold is 18% gold, or the jewelry is 18% gold. So that basically means you got 18 grams of gold for every 100 grams of jewelry that you have there. As you go through that, you would have to look at, and here we'd probably look at which number, the 18 or the 100 for significant figures. And we probably look at the 18 here. Yeah. So again, it would probably have two significant figures. Again, that wouldn't be obviously an exact number, as you might not have 18% gold. You might have 2% gold or no percent gold, right? 1 gallon of gas, 240. You see when this book was written, that was probably expensive back then at 240. All right, I'll take that if we can find where that at. But so that gets us basically $2.40 a gallon of gas. Our 1 gallon of gas was 240. Some of us remember it cheaper than that. That was expensive at one point. All right. So obviously, we want to make sure that we use our conversion factors correctly. We want to also make sure that when we use them in a calculation, we understand whether or not we have to sort of look at them in terms of significant figures or not. And again, as you see in there, so there's really kind of two places where you do have to sort of look at the significant figures, as we've been talking about. Again, if you go metric to English, or if you sort of get some type of conversion factor that was sort of given to you specific for that problem. And that does happen in a lot of problems, kind of word problems. They just kind of in words kind of give you, they'll say it's a conversion factor, but they kind of give you that information that you can use as a conversion factor. All right, so clearly we've sort of talked about problem solving, which is a same thing as really the fancier name, which is dimensional analysis. And again, this is the way that when we say show your work is really what you need to do to show your work. And it is how we've been doing it there. Here are some really important steps, and sometimes it could kind of help you along the way. Sometimes people really like to write, what's given to you. And that's really oftentimes in not just say conversion factor type problems, but in any sort of chemistry problem. And oftentimes it's a really good idea to read the problem and pull out the information, label what those units are. And a lot of times, for example, we see this a lot when we get to like the gas chapter. In the gas chapter, there's a number of formulas that you have to use, different gas laws. And a lot of times, for example, if you just pull out the information of what is given to you and label it, you label it like, hey, this is a volume or this is a pressure, and you got that thing. A lot of times it will actually point you in the right direction of a formula if you need to use a formula or something like that. So it oftentimes can kind of point you in the right direction. Could also, for example, if you're doing something like density and you see, oh, I got like density given to me and I got volume given to me. Really, the only thing I don't have with density is mass. Seems like a good place to start, probably. That's like probably a good place to start and try to find your calculation. So write what's given. You can think about what you're trying to find. And then you want to sort of think about, like I said, sort of the pathway to get you there. Sometimes the shorter pathway is probably a good one, less room for error, hopefully. But you want to look at equalities. You want to see, again, how you could kind of get to whatever unit you're looking to get. Two, once again, especially with conversion problems, there could be multiple sort of pathways depending on sort of the conversion factors that you choose to use. As I mentioned before, as long as you choose correct conversion factors, nothing that you make up, you know, they all should get you to the same answer pretty much at the end. Once you do that, you want to think about the conversion factors, and then obviously you want to set up the units as we've been doing in these problems that we could clearly see, obviously, everything canceling out through dimensional analysis. All right, so if a person weighs 178 pounds, excuse me, what is his body mass in kilograms? So obviously in this case, we have pounds and we want to get to kilograms. So that is something that we want to think about. Is there a way to directly do that? And there is. There is a relationship, right, between kilograms and pounds that you could find on that table, or we could just flip the slide here and find it on the next slide, which would be good. And we could do that, and we could see that in 1 kilogram, that is 2.2 pounds. So again, that is going to be our equality. That in this case is basically a one-step process that will get us to our answer. That's going to give us our 2 conversion factors here that we could use. And at this point, what we want to do is always start with what was given to us, which is 178 pounds. Once again, we want to think about dimensional analysis. So if it helps you, you don't have to put the 1, but if it just helps you visualize sort of where the units are, you could put it over 1. And again, now we get to a point where, as we've been talking about, we don't have to think too much about it, right? We could clearly see pounds are up on top. We want to get rid of pounds. So opposites is what we have to remember, right? So we're going to grab the opposite conversion factor that has pounds in the opposite location. We're going to set it up and put that guy in the opposite location, which would go on the bottom, and up on top here would go kilogram. Once again, the pounds here will cancel. And at this point, we would do our dividing. We basically got 178, and we know we're just going to multiply on top. So we have 1, which we really don't have to do. We're going to come back and divide by what's on the bottom, which is 2.2. And that's going to give us on our calculator 80.9090991, right? Kilograms in this case. So now we want to look at everything that we used in this calculation. Again, because we set it up as dimensional analysis, we only multiply and divided, which means we're looking at significant figures. We know now from our number of times we've seen this guy, this is a metric to English conversion, which means we do need to take the significant figures into account. Again, we're really going to kind of look at this number, and that number has 3 significant figures, right? We're going to look at our original number, which has 3 significant figures as well. And that is the lowest number of significant figures in this case. It is 3. So that is why we know we should end right about there at that 9. And when we look at the number next to it is 0, which means we just drop the rest of the numbers. And that is how they got down there, 80.9 kilograms as our answer. Any questions on that there? So if it helps you to write the equalities out, you could do so. If it helps you to write the conversion factors out, you can do so. For full credit on an exam or quiz, what you do need to show is pretty much this, yeah, or pretty much what we did up here, yeah. So you need to show the setup showing dimensional analysis with the units canceling and the appropriate conversion factors, and you need to give your answer to the right number of significant figures. But again, if it helps you to sort of write out at all the equalities, what you're looking to find, do it. What do you care? Just some paper, right? But again, you don't necessarily have to show all the conversion factors or all that in any of these problems. For full credit, you just got to show the setup and the correct significant figures. Yeah. Any questions on that? Okay, we're going to continue on here. Any questions so far on what we've been talking about? All right, let's take a look at a few others here. So a rattlesnake, is 2.44 meters long. How many centimeters is that? So again, we want to think about the units we're starting with, which is meters, and we want to highlight it apparently. Well, let's try that. That's meters, and we want to end up with centimeters. So again, we want to think about an equality that's going to get there. And I think we saw it a few times along the way. There are 100 centimeters, right? And 1 meter. That again, it's going to give us our two conversion factors that we could use: 100 centimeters over 1 meter, or 1 meter over 100 centimeters. And again, we're going to start with our original number here, which is in meters. And because it's 1 unit by itself, we know the meters are up on top. So again, we're going to get rid of it. So we're going to use the conversion factor there, where meters is in the opposite location. And again, we know at this point we can multiply what's on top and divide by what's on the bottom. The meters on top and bottom will cancel each other out. And again, if it helps you, you can put a 1 over the first number there just to visualize it. And that means we're basically going to take here 2.44 times 100. That can give us 244 centimeters. Now, when we look at it, do I need to worry about this conversion factor in terms of my answer? Yeah, for significant figures. I don't. Again, that's going to be an exact number, so we don't need to worry about it. That defaults us back to our original number, which has 3 significant figures. So we should end up with 3 significant figures at that point. Any questions on that one there? They agree, so that's good. Now, obviously, as we talked about, you may need more than one conversion factor. You may have multiple units that you're dealing with, so you just want to keep track of things. So what do we got going on here? We got a doctor ordered 0.15 milligrams. If you only have 50 microgram tablets, how many tablets are required in this particular case? So we've got a couple of things sort of given to us. In this case, we do want to give the person 0.15 milligrams of it. And we only have tablets that are 50 micrograms per tablet, basically, right? That's really a conversion factor, right? We can also flip it around and do a tablet is 5 micrograms, right? We have the base unit of grams in each of them, but this is milligrams, right? And this one is micrograms. Can we use them like that? We cannot, because they're not going to properly cancel out. So this is a situation where you really have 2 options as to how you want to do it. One option, which is probably, I would say, maybe the best option, and maybe, is just simply convert first our milligrams into micrograms, right? And now we're good to go with whichever sort of conversion factor that we need. The other option would be you can leave your milligrams, but convert the 50 micrograms into milligrams, and that's the other option, and then use it as a conversion factor there. They both should sort of work. It's just sort of what you want to do. But we do need to look at, some conversion factors between micrograms and milligrams, which we have here. So we have 1 milligram is 1,000 micrograms, which gives us our 2 conversion factors. We also have, obviously, our tablet conversion. So we're going to start with perhaps here taking our original value. And really the purpose of this conversion is just to get it in the right unit so that we can actually use the other conversion factor with it. So we still do the same thing as normal. We just know we need to get rid of milligrams. So we want milligrams in the opposite location of top. So we do want to use this guy here. And that's going to give us 1,000. Going to give you micrograms and 1 milligram. The milligrams will cancel. Once again, we know we're just basically multiplying here. There's really nothing to divide on the bottom since they're all ones. If you want to put 1 in your calculator, you can. Nothing will change. 0.15 times 1,000. That's going to give me 150 micrograms. Now that is good because now I could actually figure out, right, how many tablets I need to kind of roll with in this particular case. And in this case here, we also want to go opposites. We want to get rid of micrograms, right? And we eventually want to figure out tablets. So that is really this equality that's going to allow us to do that. So we can set it up the same way. Again, we can put that over 1 so we could clearly see micrograms again is on top. And that means opposite to cancel. So we would need micrograms on the bottom, and that would give us 1 tablet on top and our 50 micrograms on the bottom. Micrograms are going to cancel. That's going to get us here 150 divided by 50 in this case. And that is going to give us 3 tablets. Now, in terms of significant figures, what should it be? Well, we do need to look at this number, right? Which technically has 2 significant figures. Our original number that we converted, which is over here, has 3 significant figures, which means really, although I didn't really write it as 3 significant figures, I probably should put a decimal there. Now we have 3 significant figures divided really by 2 significant figures. Really, the answer should be 3.0, right? They go with 3 tablets because you're probably not going to break a tablet in real life and go and can get like the point something on it. But really, if you're going strict significant figure wise, it really should be 3.0. But they, looks like in the book, went with just 3 tablets in this case. Maybe they did that because, again, you wouldn't probably be breaking tablets in half or something like that if you didn't get that. But it will go with strict significant figures. If you go strictly by significant figures, you really should end up with 2 significant figures in this particular case. Any questions on that one there? Yeah. Test or exam, I would say go with strict significant figure rules. We'll leave sort of real life out of the play, I suppose, right? Because get a pill crusher or something like that to crush a half of or a little bit more of a tablet. So I would say in this case, just in general, just go with probably strict sig fig rules and you'll be okay. I will say though, you might want to be a little careful on a question like this, maybe online in the Mastering Chemistry. Again, I don't program it, so depending on how it was programmed, they may do kind of a similar thing in an answer like that. If it's something like how many pills you may give somebody or something like that. So I would say first start with real significant figure rules, following them. And then maybe if it's a question online that kind of throws that answer out, then just kind of default back to, okay, maybe they just want like how many whole tablets it would be in that case. Other questions? Yeah. All right. How many minutes in a day? Let's hope so. I don't know. So again, we want to think about how to get there. We got days and we want to end up at minutes. So again, you could go there is in 1 day 24 hours, right? And 1 hour is 60 minutes. These are our 2 equalities that we could have. So both of these are equalities. That will give us 4 conversion factors to possibly choose from here. We could go 1 day is 24 hours or 24 hours is 1 day. We also could go 1 hour is 60 minutes. Our 60 minutes is 1 hour, right? So if we start with, again, what is going to get us there, we're going to start with our days. And again, we could kind of throw 1 over there and see days are up on top. We obviously could go from days to hours and then take our hours to minute as our sort of game plan of how to get to the end. So we want days in the opposite location. So that's going to be that guy right there. That's the only one where days is in the correct location. Those are going to cancel. Again, if I stop my calculation right at this point, I'm in hours. And again, by setting it up like this, we once again can clearly see hours are up on top. So we got to go opposite to get rid of it. Makes the decision a lot easier at that point. I'm just going to find my hours in the opposite location, which is that one, right? And then put it in. Hours will cancel. Once again, at this point, we're going to multiply everybody on top. We're going to come back and divide by the bottom, although there's really nothing to divide by since they're all 1 on the bottom. So it's going to be 1.6 times 24 times 60. That's a 2304 on the calculator. Significant figure-wise, we should end up where? Yeah, we don't have to worry about this guy. We don't have to worry about that guy. That means that's the only one we do have to worry about, which has 2. And that means we should end up there. So I think you said 2,300 minutes, I hope. Yes. So if you didn't, that's what you should have said. That should have been 2,300 minutes. Any questions on that one? Obviously, we could also do scientific notation if you wanted to. Be 2.3 times 10 to the 3 in that case. Yeah. Any questions on that there? All right, let's see what we got going on here. 2,300, they agree. That's good. All right. All right. Your pace on the treadmill, 65 meters per minute. How many minutes will it take you to walk a distance of 7.5 kilometers? Give it a go. See what you get them up with here. Set it up, dimensional analysis, think about what you need. I see kilo, right? Which is 10 to the 3, right? Which is 1,000. It's really a conversion factor in the actual problem. So you could use that as a conversion factor of 65 65 meters per minute, or in a minute you have 65 meters. It's really your rate, right, of how fast you're moving, like how fast you're driving. And that's really what's we're going to use as a conversion factor to go from distance, like 7.5 kilometers, into time, which is minutes. So we need a way to go from obviously from distance into time, and a rate, which is how fast you're traveling per se unit of time, is allowing you to do that. We also have 7.5 kilometers. Can I use my 7.5 kilometers and these conversion factors the way they are? I cannot, because my distance or length unit is meters here, while my distance unit here is kilometers, which means if I try to use them together like that, I'm going to be off by like a factor of 1,000. And that's not so good. So you do need to get everybody always into the same units if you need to get rid of them or cancel them out. So once again, we have a couple options as to how to do that. You could either take the meters to kilometers, or you could just simply take the kilometers to meters and then use the conversion factor. That's what I'm going to do. Once again, if we look up kilo, that is how much there is in the base unit to one of the prefix units. So that means in this case, 1 kilometer would be 10 to the 3 meters, right? Or 1 times 10 to the 3, or 1,000, basically. Yeah. That's our equality, which gives us our 2 conversion factors that we could use. So starting with our 7.5 kilometers, the goal here is just to get it to the right unit so we can use it again. We're going to again see that it's on top, so we're going to go opposite. So we want to use the guy on the right there. That's going to give me 10 to the 3 meters is 1 kilometer. Kilometers will cancel. We're basically just multiplying the top, 7.5 times 10 to the 3. No negative. 7,500 meters in this case. Now we have it in a unit that matches the units that we see in our conversion factor. So we just continue to do the same thing, which is, although I have meters, I don't want meters. I eventually want minutes. So I want to get rid of those meters, which is now on top still. So again, allows us to very simply figure out which one we need to use, which is the one where meters is in the opposite location. We get 65 meters per minute. Meters cancel. We're going to multiply, which you really don't need to do because there's nothing there to multiply it by but 1. But we're going to divide it, more importantly, here on this case. So we're going to take 7,500 basically and divide it by 65. Dare I say that is a 115.384. That's a lot of numbers. Don't give me all those numbers. That's how many minutes. So how many numbers should we end up with in this case? Should be 2. We do need to look at this number, which has two significant figures. That means when I did the conversion, I still had two significant figures, which I should have. That means I have two significant figures here. And we do need to look at this number and this conversion factor, as that's not an exact number. And that would have two significant figures. That's going to bring me here. So I'm going to end up with like $1.20 here, 120 minutes. Yeah. No decimal. Otherwise, it's got three significant figures in this case. Yeah. Any questions on up there? Again, also could do scientific notation 1.2 times 10 to the 2 in this case. Yeah. Any questions on that? Yeah. If you put in scientific notation, no, it's fine. Yeah. Yeah. So you can always use scientific notation if you want to use it in every answer, but you can definitely use it. Yeah. So it would not be wrong as long as you did it correctly in the correct scientific notation. Which would be in this case 1.2 times 10 to the 2 minutes. Why did I not write 1.20 times 10 to the 2? It would then have three significant figures, right? So again, there would be no problem if you did that for any answer. You could always do that if you want. Yeah. You just want to make sure you watch the significant figures, obviously, when you put it into scientific notation. Other questions? All right. Hey, they agree. That's even better, I suppose. All right, let's try another one here. Why not? You go to AM/PM, get yourself a 32 fluid ounce drink of Diet Coke from the Thirst Oasis. Crushed ice, cubed ice, your choice, but everybody takes crushed, don't they? There is no choice really at that point. You take crushed ice. All right, so we want to know how many gallons of Diet Coke did I just drink? Here's a couple of equalities that might be helpful for you. So see what you come up with, set it up. Okay, so let's take a look. Again, here we're starting with 32 fluid ounces. We want to get ourselves over to gallons. Again, one pathway here is some of the equalities that I chose. We could go from fluid ounces to quarts. Once we have it in quarts, we then can take it to gallons at that point, is sort of the pathway. Those are our equalities, and obviously we could have a number of conversion factors here to choose from. So here we will start with our 32 fluid ounces. And once again, we can see that it's on top. So again, makes the decision pretty straightforward. We got to go opposite. So that's the opposite location for those fluid ounces. So we'll go with 32 fluid ounces on the bottom, 1 quart on top. If I stop the calculation right at this point, the 2 fluid ounces will cancel each other out. The only unit left at this point is quarts. And again, we could clearly see at this point that it's up on top. And that makes our second decision also relatively quarts bottom location, right? So that takes care of that. We're going to back up the next calculation there. 1 gallon. Quarts will cancel and divide. It equals, and you end up with 0.25 gallons. You do not end up with 1/4 because it makes me think you're too lazy to divide it. So don't leave it as a fraction. Yeah, actually get a number and do it. Yeah, that's not too bad, but I have had people write answers like 365 miles over 4,244 hours, and it looks good. We're supposed to divide it. Yeah. So what you want to do is basically all you have up on top is 32. If you multiply it by 1, you still get 32. You want to divide it by the 32 on the bottom, and then you want to make sure you hit equals. And then you want to divide it one more time by the 4, and then hit equals. Yeah. So again, when you have multiple numbers on the bottom, don't be afraid to use your equal sign multiple times, and you'll get the right answer that way. So divided by the first number, hit equals, divided by the second number on the bottom, hit equals. There's a third number, divided by the third number, hit equals. You will always get the right answer if you do it that way. If you decide you want to try to throw them all into your calculator at once, you probably will get the wrong answer if you do not put it in correctly, which is a very common mistake that people make. They try to put it all in at once. And if you're not really careful with parentheses, you will get the wrong answer. The way you always get the right answer is basically just do each one individually and hit equals after each one. So divide each one, hit equals, divide by the next one, hit equals, and so forth. Yeah, so that again, that's the beauty of sort of the dimensional analysis we've been talking about. And that's what I was saying before, where it just kind of takes the sort of thinking out of what you need to do thematically when you set it up like this. All you have to remember really is three things when you set these type of problems up. You have to remember that anything on top gets multiplied, anything on the bottom gets divided, and if you want to get rid of units, opposite location. And then you'll always do pretty much all the correct math. And you don't ever have to think about, should I be multiplying, should I be dividing? All you have to remember, it's on top, multiply, it's on the bottom, divide, opposite units, cancel. Other questions on that? All right, let's take a look at that one. Patient receives 5 pints of plasma, milliliters. Well, we're getting that might be helpful. Okay, so again here, we're looking from pints and we want to get ourselves to milliliters. This obviously could be one pathway, pints to quarts and quarts over to milliliters. So we will start with our 5 pints, which once again, if it helps you can put a 1 so you can see it's on top. Do you have a question? Or... Okay, yeah. So we want to start with the opposite location, which is pints on the bottom and a quart up on top. That's going to get rid of our pints. And once again, we're going to be at quarts at this point. Again, we can see that it is up on top. So opposite location to cancel. Going to use that right there. Those will cancel. Going to leave us our 1 unit that we need, which is milliliters up on top. We're going to multiply everything up here on top. Again, divide by the bottom. And that basically means we're going to take 5 times 946 divided by 2 in this case. That's going to give us 2365 milliliters. We now want to think about our answer in terms of significant figures. Do I need to worry about this conversion factor here? The answer is yes. That is a metric to English conversion. So we need to look at 3 for that guy. How about this one? That one is no. That one we do not need to worry about. That's okay. And we do need to worry about the original number here, which is 2. That means our answer should end up with, yeah. So again, that's going to bring us back over here. So we want to make sure we round correctly. That's going to bring us to 2,400 milliliters. Or you again can do scientific notation, which will look something like that if you choose. Yeah. Any questions on that one there? Yeah. You do. Yeah. So you basically up on top, you're going to basically take 5. You don't really need it times it by 1 because it's 1, but if you want to, you can. You're going to times it by 946 and hit equals. You then are going to divide it by what's on the bottom, which in this case is 2, hit equals. And you really don't need to divide it by this number because it's 1 as well. So you'll get, the same answer. Yeah. Other questions? All right, let's try this one. This sounds like fun, maybe. You are stranded 125 miles away from home. You have no money. You decide, seems like a nice day. Let's take a walk, right? You walk an average of 55 feet per minute. How many days will it take you to get home? Does yours say 55.0? About a curiosity on your paper? It does. I'll change it to yours so it matches. So yours, I think, says 55.0. So we'll make that 55.0. That way we're both looking at the same thing. All right. All right. See what you come up with. How many days am I walking? And we do have a rate at which we're walking, which is 55 feet per minute. That rate is what's going to, again, allow us to kind of turn into time from distance. We can use that conversion factor as it's given to us in the problem. We could also, again, flip it around the other way if necessary. We once again have a similar situation that we saw earlier. We can't really use both of these guys together, as the length part, distance part of each of those values are different units. So we do need to find a common unit to use. I am personally going to use miles and convert them to feet. And once I do that, I then can kind of choose the right conversion factor to use. Again, I cannot use the miles and the feet together because they will not cancel out correctly. They got to be the same unit to cancel. So I'm going to start with this equality that allows me to go from miles to feet. Just going to do a very simple little conversion. Again, miles up on top. So opposite means I need to put miles in the bottom location. And up on top will go 5,280 feet. The miles are going to cancel. Once again, on top we're multiplying. So we're going to take 125 times it by 5,280. And that's going to give us something like 660,000 feet. You will get your steps in today, I guess, as you're walking home. Now that I do have it in feet, that's going to allow me to very easily use my rate, which are feet per minute, to get me to time. Any questions on that so far? So that's what we're going to do. I'm just going to carry over the whole number here. I'm not going to really worry about sig figs or anything like that at this point. This again, it's on top, so that makes my decision as to what one I should use easy. Feet are on top. I need to get rid of feet. Feet need to go on bottom, so I need to use it actually like this, which puts it in the correct arrangement there. That's going to allow the feet to cancel. If I stop it right this moment, I am in units of minutes, which is close to what I want, but I want days. So maybe I need to go from minutes to hours. Once again, minutes are on top, which means 60 minutes need to go on the bottom to cancel, is 1 hour, which is the conversion factor that we get from there. Yeah. That will cancel the minutes. I am now in the units of hours. So again, close to what I need, but I need to go one more. That is where this guy is going to come into play. Opposites again cancel. Hours on top means my 24 hours go on the bottom. My 1 day goes up on top. The hours cancel. Again, I can't tell you how many times people, when they do not set it up like this, will be doing the opposite math, the wrong math, and put things in the wrong location. Again, at this point, all we have to remember is everything on top gets multiplied. And in this case, everything on top is 1, other than the original number of 660,000. So you don't really need to multiply by it. Here we got 3 numbers to divide by on the bottom. We're going to divide by this. Again, I would recommend hitting equals after each time. Hit divide, hit by 60, then hit equals, divide by 24, and then hit equals. Obviously, divide by 55 and hit equals will be the first one. So we're going to divide our 660,000 by 55, hit equals, divide it by 60, hit equals, and divide it by 24, hit equals. And on your calculator, you will get 8.3333, maybe a few more threes, days in this particular case. Now we want to think about what our answer should be in terms of significant figures. Do I need to worry about this conversion factor? No. How about this one? No. How about this one? Yes. And how many significant figures does this one have? It does have 3. That I used the corrected one like you have. I do need to worry about this one, right? This one I actually originally started back over here, which has 3 significant figures, which means really this number, although I didn't write it with 3 significant figures, should be 3 significant figures, which means this number technically again should still be 3 significant figures. And that means that our answer should end up 3 significant figures. That's a lot of walking, 8.33 days, and you'll be there. If you don't stop along the way, I suppose, and just keep going. Any questions on that? So again, although I did convert the first one into 660,000, which the way I wrote it is 2 significant figures, in reality, it should have had 3 significant figures. So these are things you got to kind of keep track of as you're doing your calculation. Sometimes you do that. Sometimes you just take the number you have and just think about what it should be without rounding. Yeah. You should, I be honest with you, the safest rule usually is don't round to the end. Yeah. So take all numbers that you get. So if you do calculations in parts, What I mean by that is like you do a calculation, get an answer, take that answer, do another calculation with it, get an answer, do another one. Perfectly fine to do. But every time you get an answer and you're going to kind of take it and do another calculation with it, I would take it to a few extra digits than it should be. So if you want to write down a number, for example, that's 660,000 really, right? And it should be three significant figures. I could have wrote, 6.60 times 10 to whatever it is and have the right number of significant figures. But in general, I personally like to roll with the number in the calculator and just keep going with it. But if you do want to write something on the paper, I would figure out where you technically should stop and keep an extra few digits until the very end, and then you should clean it up to the right number of significant figures. And that's really the best way to avoid rounding errors. So if you did the first one and like strictly rounded, which maybe in this example wouldn't be too big of a deal, and then you did say this part of the calculation here and got an answer and you rounded a lot, and then you took that number and did this part of the calculation and rounded, by the time you get to the end, you'll be pretty far off because you're adding rounding errors along the way. So you don't really want to round really strictly until the very end. If you want to keep a number or write a number, you should keep a few extra digits than what you need. So for example, if it's like two significant figures, you really should have maybe go a few extra digits and keep them until the very end and then round at the very end. And that usually will avoid any type of rounding error. Yeah. Yeah, so if you're rounding, so if your question is this, that the answer was like 8.333, a bunch of threes, obviously. And we want to stop here, basically, right? So what you always want to do is figure out where your answer should be. So in this case, we want to stop at the third significant figure. You then always want to look at the number next to it, okay? Now, there's two things that you will probably do in that situation is, in this particular case, because it's less than 5, we really just drop the numbers. And that gives us something like 8.33, like the answer is, and that's three significant figures. If that number, for example, was 8.3336, right? We would look at this 6 and then, actually, I went too far. We'll put a 6 there as well. We'll look at this 6, and then we would know we would need to round up, and we should round to 8.34. Now, I think the question that you're probably both are probably asking is this question, which is, let's say we had 82465, for example, right? And we want two significant figures, right? In this case, we would still do the same thing, which is we would look here, and that's where we want to stop. So we do want to look at this, which means technically in this case, it's less than 5, right? Which means we drop the numbers. So if we drop the numbers and just write 82, we have a problem because what did I just do? It's not the same number, right? 82 is very different than 82,465, right? So in this situation, which I think was your question, like when should you add zeros? This is a situation where you would want to add zeros. And the reason we're adding zeros in this case is now we have 82,000, which keeps the meaning of the number the same, but we also still have two significant figures. So in this case, because if we just strictly round by dropping the number, we actually change the meaning of it. You do have to add zeros in to keep the meaning what it is, or you might have to do scientific notation. The reason we don't have to do that on this answer is when I just drop these numbers, 8.33 is pretty much the same thing as 8.3333, a bunch of threes, right? It doesn't change the meaning of that number. So you're safe to just drop them. You don't have to add extra zeros because unfortunately, in that case, if you added extra zeros, now how many significant figures do I have? Yeah, if you round it to 8.30, that would be incorrect in this case because we wanted three significant figures, right? And when we looked at our original number, wherever it went there, our original number looked like this. That is our third significant figure where we want to stop. So you always want to figure out where you need to stop in terms of significant figures, but then you got to always look to the number to the right. And that means that the only number that would ever be affected would be this number if it was affected. And you can't just make that a 0 at that point because that's not rounding correctly in this case, because you should just drop the numbers in this case. You're free to drop the numbers in this case because it doesn't affect the meaning of the number. But if you are going to drop the numbers and it affects the meaning, like my original example up here where I just dropped them all and called it 82, you can't do that. You got to add some zeros to maintain the meaning of the number. Other questions on that? Yeah. I will say, if your question is, you are responsible typically for formulas. We really haven't had formulas, but you would be probably provided, for example, the equalities, like there's 5,280 feet in a mile. The conversion factors would not be provided for you. Hopefully you know how to write those, and then you would use it that way. So you would be provided like the 5,280 feet is a mile. I don't know, maybe like I said, I provide maybe the minutes and hours. Hopefully you know some of those, but you know, those type of things are, there's 453 grams in a pound would probably be provided for you, but you wouldn't be provided like the conversion factors like this over this or this over this. From those equalities, you need to know how to kind of turn them into conversion factors. Other questions? Yeah. If your question is, do I care if you do it all in one calculation or if you do it step by step, get an answer? I personally don't care as long as you show the work. So if you did, for example, like I said, if you kind of broke this up into separate calculations, just did this part, is perfectly fine as long as you showed the work and you get the answer. Again, I would not round at that point until the end. And then you took that answer and did this part of the calculation. And then you took that answer and did that part. It's perfectly fine. If you want to do it in pieces, you want to put it all together in one calculation, including, by the way, the first one there where we had the 5,280 feet, and you set it up correctly that all the units cancel. It's all good. So I'm okay if you do it piecework. I'm okay if you put it all together. The end result is you need to show the work with the conversion factors. You need to have the right number of significant figures at the end. And again, if you just do piecework, just make sure that you don't do too much rounding until the very end. Yeah. Other questions on that there? Question on conversion factors or anything like that? All right. So like I said, the equalities will be provided for you, not really the conversion factors. And again, you do need to show your work along the way.